Good afternoon. How are you guys doing today? Good conference so far? Yes? I've been seeing a lot of really good activity. A lot of people excited about what they're doing, excited to be here, and I think that's awesome. So, my name is Brian Finley. I'm the Principal Architect for Big Data Solutions at Lenovo. We are part of the organization at Lenovo that was acquired from IBM as the System Max or Enterprise Server Division, which included high-performance computing and other complex solutions like that. So, to introduce you to me a little bit, let's start with the agenda. We'll talk a little bit about, who I am, where I'm coming from, and how that may relate to what I want to talk about. I'll give you a proposition, and then we'll talk about Spark, which is a software solution that's included in that proposition. And then we'll take a look at a potential architecture that could be used to take advantage of that. My name is Brian Finley. I live in Texas. I have one wife. Just in case you're wondering, this is the way to go, just one. I've got one 17-year-old, three 10-year-olds. We were talking about identical twins before. The two on the outside edges are identical. The one in the middle, fraternal. That's kind of cool. They don't always look like that. I had my first introduction to bioinformatics at UT Southwestern Medical Center back in 1992. I was working with a couple of labs that were doing genetic engineering research, one on retroviruses and another one on other autoimmune diseases like diabetes mellitus and things like transgenic mice with Nadine Toyon. And for anybody who might recognize the name, that lab was with J. Donald Capron. And that's where I got introduced to this thing. So this is really old school, right? Does anybody still use these anymore? Okay, well, I was the computer guy in the lab, and part of what I was responsible for was maintaining the computer systems that tied into all of the bioinformatics equipment. And sometimes I actually got into inputting the sequences with the light pin on the light board. Yeah. Very tedious. Not necessarily particularly accurate either. But we made progress. So jumping ahead many years, in 2002 I went to work at Argonne National Laboratory and participated in a number of things there, including I was highly involved in the TerraGrid. We were one of the first 4 sites, and Indiana University was also one of the sites, so a lot of good tie-ins there. In 2011, I went to work for IBM. In 2014, again, my business unit was acquired by Lenovo, and here we are. So, that's where I'm coming from. I find it often helpful to know who's talking at me when I'm listening. So, my proposition is that we look at incorporating Spark into the Galaxy ecosystem. This would be the ability, Galaxy has this workflow with the ability to execute multiple tools within the workflow. And the idea would be to modify Galaxy to be able to support Spark-enabled tools as the first pass. Now, Spark also has the ability to do a workflow kind of job. So later on, with additional effort, things could be modified so that you had tools as libraries, if you will, that could be combined together ad hoc by their functions to create a single job that would execute the entire workflow within Spark. Now, why would you want to do either one of those things? And the reason is that Spark is designed to do a couple of things that I think would be beneficial for Galaxy. One is it enables scalability in a dramatic way. The largest Spark cluster that I'm aware of is running on 8,000 nodes. But unlike with our classic HPC systems of today, where in order to truly take advantage of all of that parallelism, you have to really understand how to write parallel code, which can be very complicated. And if you are more focused on the research, that's really what you should be focused on, rather than on being a parallel programming expert. And so Spark brings some ease of use to the coding model that could be really handy. So once you have enabled a tool to execute within the Spark framework, it can run on your notebook. You can also run that same tool unmodified on a large cluster. So, what is Spark? It's an open source framework or an engine that allows execution across many machines in a cluster. And again, you can run it on a single node. As I mentioned, it's easy to write Spark-enabled code that gives you parallelism without you having to be a parallel expert. It provides native libraries for a number of languages, including Python. And it came from the big data space. So it was an outgrowth of all of the activity that's happening in the big data world. And when I think of the big data space, I think of it as being, with having Hadoop at the center. And you may recognize some of those logos up there. These logos represent the 4 primary big data distribution vendors. And inside each of those big data distributions is Hadoop, as well as Spark. But Spark is designed, although it's designed so that it can work with Hadoop, it doesn't have to work with Hadoop. So it can work with, in the primary reason why that's important today for us is that when you're working in a Hadoop environment, you're using the Hadoop file system, or HDFS. And HDFS brings along with it some things that make it a little bit more difficult to start working with. They're a bit of a barrier to entry, if you will. Primarily, that the file system is accessed through an API that is, it's not just like a normal file system or a POSIX-compliant file system that you would have on your desktop or on a normal server today. And so what I would be proposing is, this is the way a Galaxy node would look today. And what I'm proposing is that we use a model that would incorporate the ability to leverage Spark, but without having to also do the forklift changes that would be required to take advantage of the HDFS file system. So today, if you look at a Spark node, a Galaxy node, you have the Galaxy software running on it, and you have a local file system, and Galaxy is expecting to find all of the data for the jobs that it's going to run throughout your workflow in that local file system. Now, what if we were to Spark enable a tool? Well, it would then look like this. All you have to do is have Spark on that same node. Now, this doesn't represent that Galaxy is sitting on top of Spark. It simply represents that the two of them are in the node together, kind of side by side. So at this point, the only thing that's really different from the perspective of a user is there's one more package that's been installed. And if there's a tool that's already been written that leverages Spark, they don't really know any different, and it doesn't really matter to them. But what if we were to extend that file system out so that other nodes can get access to it? And this could be done with something as simple as NFS. It could also be done with GPFS or Lustre or any shared file system that just looks like a normal file system from the perspective of all of the nodes. Then you can simply add one more node with only Spark installed. Now, when you go to execute that tool in a workflow, that tool executes across all of the Spark-enabled nodes in your cluster. And so the tool that was incorporating the libraries and the code modifications that you made once for that tool that work on your local system, you're now able to expand across a cluster that will scale to the size of your budget and beyond, and you don't have to make any code modifications past that point to do it. So, in contrast, this is what HDFS looks like, where you have data, the little chunks of yellow represent data that's distributed across disks across many different nodes. Now, this is great and provides an even greater level of scalability than what you can get from your typical shared file system, but it does require access through that API. However, because Spark is able to use a normal POSIX file system or HDFS, once you've written the code, if you get to the point where you want to move onto a larger system that's using HDFS as the file system, you're already prepared to do so. Thank you very much. And do we have any questions? That's awesome. I'll be expecting code examples at the end of the day. So,
I'm an HPC person, and I'm not that deep into Spark. And what makes it very interesting for me is that Spark parallelize code without having experience with code parallelism, which is one of the main problems that we face with scientists in operations.
Yes.
So I didn't get it quite right. If someone write a serial code, this is a serial code, and it has to be parallel code in order to run in parallel.
Yes.
So is there some code parser, for example, or code optimizer inside Spark or something? How is this part is done?
Yes. So let me repeat the question first. The first part of it was the statement that I completely agree with, that one of the challenges we have in HPC today is researchers being, in order to fully take advantage of the machine, you have to have the ability to write good parallel code, and that's a challenge. So the second part is, if you have something that is serial in nature, how do you parallelize it, and how does Spark handle that? So the answer is that there are a lot of serial operations that can be done if you were to break it up yourself in advance. Let's say you're indexing a very large sequence, okay? You could manually say, well, I'm going to break it up and I'm just going to index, the first third of it today, doing it by hand, second third tomorrow, and so on. Spark is able to recognize that the data that holds that sequence is available on multiple machines. It's also able to recognize that the function that you have called within Spark to read in the data or to process it is that type of function, something that is serial but parallelizable, and it's able to distribute the workload to say, these threads on this machine are going to handle this portion of the file, these threads on this machine are going to handle this portion of the file, and so on. Once it gets interim results, it stores those in memory, but not just on the machine that did the calculation, but that in-memory result is distributed to other machines, and that's called a residual or a resilient distributed data set. So now, for the next iteration of code of data manipulation, any of the machines or all of the machines that have access to that data in memory on themselves can then participate in that next iteration of processing. Does that help? Sure.
So as I understand it, it is, but you need to do something. You need to define these threads. For example, you cannot write a simple matrix multiplication code that makes matrix multiplication within a loop, and then it will modify your code to make this loop parallelizable. You need to define some threads for this to be doable.
So I'm having a little difficulty hearing from the mic and the echo, but
you need to basically define how Spark is going to be able to parallelize that, develop
Spark figures it out based on the functions from its library that you call.
So there is no developer effort on modifying any part of the code which can be parallelizable. Spark does all of the thing, or you need to do some modifications. This is
Spark does it. Spark does it for you. So it's important that you understand the workflow of the job, and based on that, you write the code to handle that workflow within that tool or that job. But once you've done that, within that workflow, each step along the way, Spark handles the parallelization where possible.
Okay, one last small question. Is that engine can work on the top of existing queuing system, Slurm, for example, or it has to?
I'm sorry, I missed that one.
Maybe this is not very...
Yeah, I think it's just the echo.
Can Spark work on the top of Slurm, for example?
Yes. As a matter of fact, at Lenovo, we're currently we're doing a collaboration with the Barcelona Supercomputing Center, and one of the work projects that we're leading is to determine the efficacy. How reasonable is it from a practical use perspective to launch Spark jobs on a classic HPC resource using Slurm? And we have a lot of existing HPC customers that are starting to try to do things like that. Thank you.
Great, thanks. So real quick, so in terms of deployment, if one were to integrate Spark into Galaxy and then want to deploy this in their local environment, is there any other sort of resources one would need on their nodes in order to deal with the added sort of memory requirements and keeping things in order for this reduced step or whatever it's called?
So Spark handles a lot of that for you with auto-tuning, but fundamentally there's a master and worker processes. And when you launch a Spark job, the master process will coordinate across the worker processes, whether they're all on the same machine or across many different machines. Yeah.
Okay, great, thanks.
Very good.
Thank you.
All right, thanks guys.